Okay, as I promised you, we are going to actually start talking about mechanics finally, with all the delays, and instead of 3 weeks, spending 4 weeks on math. Now we are at the position to start talking about the strain. So to be able to make, to derive the field equations that we need in elasticity, we need to know the relationship between a strain, displacement, deformation, which we call the strain kinematics. We also need to know balance laws. If you have taken continuum mechanics, you have seen enough of that. If you haven't, I'll review without giving you proofs. So I will just go through the balance laws that we need. And then we need to have an idea about the material's behavior. In this class, everything is linear elastic, but we learn how to formulate it. And this is putting all of that together, then you can have field equations. So starting with a strain kinematics today. So what I want to do today is basically to find the relationships between a strain and displacement, to define everything we need, and to derive the equations. So we're going to talk about the strain. And my hope is that by the end of the class today, we have some relationships between a strain and displacement. So, let's start looking at a general body. So we have a body, I call this B naught, and I consider a coordinate system. This is 2D, the drawings, but as you will see, the formulation is pretty general. So we have B naught, and this is how the undeformed body looks like. So this is what we call reference configuration. And then you have forces applied on this body. Something happens that it deforms, and it also can also move. So we have the current configuration. I call this B, or sometimes you call it like BT or B. That's like the time. That's the current configuration. So this is current or deformed configuration. And in continuum mechanics, we assume that the body is made of a lot of particles, and they're very, very tiny, so it's like a continuum. And each one of them, you can track its movement and look at that displacement. So let's take one of these points. I take one point here, try to use some colors here maybe. X, and imagine, I don't know if any of you uses like digital image correlation, any kind of particle tracking. Tom is shaking his head. You are using that? Right. So Mustafa is familiar with that. So there are ways that nowadays you can actually track one particle, right? You splash some paint over the body, and then you look at one particle. So imagine that, like mathematically, we want to do that. So we want to see what has happened to this one particle. So that's the same particle, but it has been moving. I should change the position of this because I don't want to imply that the displacement vector is horizontal. So you guys know that we talked about vectors before, so this is the displacement vector, right? Which is, you remember that it's kind of always looking at movement. And the position vectors, how do they look like? Well, those are going from origin. I use a thinner line to those points. That's all I need. Okay. So now let's recall some of the things that we had before. X prime is basically the new position, the new particle, and it's a function of x, right? And how do we write this displacement vector? You are all now experts. We said that with points and vectors we use the same notation. So I hope you all agree that we can write this. Or if you are interested to see what happens in the deformed configuration, you can just say, well, we start with the undeformed reference configuration, and then if you add to that the displacement, you are going to get the deformed particle location. So now, before we call this a vector or a vector field, when I say vector field, because you can have for every single point in your body, you can imagine to have one of these vectors, right? Now it has a name, and the name is, what do we call U? Displacement field. Yeah, exactly. If you are talking about point X, would be like displacement of point X. Does this tell us anything about deformation or a strain? Because you are all familiar with the strain and deformation. This is not the first time you hear about it, I hope. Right? So what is the difference between displacement and deformation? Why don't I call this deformation and I call it displacement?
You have rigid body displacements. So if you move an object from one spatial region to another, you can do that straight through.
Is this just a rigid body displacement?
It doesn't have to be, but it can be.
It can be. So this is exactly the answer I was looking for. Displacement is not equal to deformation. What distinguishes deformation from displacement is that the body changes shape. If everything moves the way it was, you came from home or a dorm or from your office here, you are the same person. If there was no deformation, you are still the same person, you were just displaced, right? It was so cold last week that I guess some of us really shrank. No, I have seen worse. So now that we know what displacement is, and it's not the same as deformation, let's start talking about deformation. Because you know that a strain is related to deformation. So we need to kind of start to formalize that. So how do we describe then deformation? So I write here change of shape. So if I have the same body, if I want to describe its deformation, if I want to find a way, I need to first know what I'm looking for, right? How do I do that? How did we do this before? How have you done this in your life before? While you are thinking,
I'm taking gradient or measure ingredient.
you're going far ahead of me. Let's just stick to the basics. I have this body. I want to start defining deformation. I saw that if I just track one point to another point, this displacement, it's nice, but it's not that useful.
Change in shape.
Yeah, so change in shape. We all agree that's kind of what distinguishes deformation from displacement. Now, how do I quantify it? Because I want to calculate it. Remember, I don't have any equations there, so I want to write these equations. So how do I do that?
The displacement of one point on the body relative to another point on the body.
Correct. So I need to take 2 points, for example. So if I take 2 points, so now I look at my deformed body B, and I look at 2 points. I haven't called them anything yet. I will call when we are deriving the equations. And then what do I look in the other body? I know. So for example, they have become like that. What I need to look for is whether the distance between them has changed, right? And another thing that for deformation I need to look at is what? If I take another line and you have seen this before, guys, and I look at how it has deformed, what do I look? I look to see what has happened to this angle. So this was phi here becomes phi prime. So basically saying change of shape is correct, but how do we measure change of shape? We measure change of shape in 2 ways. Was there a question?
Is it stretch and rotation?
Rotation is a dangerous term to use here, because you can, for example, if you can do gymnastics, you can rotate. I can't, right? But nothing happens. You are the same person. There will be no deformation necessarily, right, with rotation. What you are thinking is probably shear, right? So the change of shape, let's just decide. We have change of length or angle. And the first one we call extension, and this doesn't mean that it has to necessarily like extend. It's more like it can there are other terms for that. And this is shear, and this is what I think Gerald was thinking about. And this whole thing is what is related to a strain. So if we want to find a strain, we have to quantify change in length and change in angle, both. And this is what we are going to do. Now, to quantify things, we always kind of, in continuum mechanics, go and look at a small element and try to see what happens to that element. And this is exactly what we want to do. I don't draw the body anymore. I just make this a small element. And this is kind of, I try to make this nice. I mean, maybe let me just, for the sake of completeness, tell you that I take the body and I just take a really tiny element out of it. And just for convenience, I take a square element. There is no reason not to take a rectangular or anything, but I just take a square to make things easier. And then I try to see what will happen to this element. We have a lot to do with this element, so I try to draw this nicely. So, of course in 2D, because otherwise I can't draw it really. Let me call the corners of this so there are 4 corners, each one has a name, and then I have to draw how this, so I consider this to be a square. I want to draw how it will look like in the deformed configuration. I don't write it down, but this should be clear. And this is really tiny. So it's a small material element. I put a small in quotation because a small means different things to different people. But this is like infinitesimal element. It's very small compared to the size of the object that you are studying. And then let's use prime for the deformed configuration, which we have x prime A, x prime B, x prime C, and x prime D. And I told you that I take a square, so this length is the same, and it's just for convenience, just to make things a little bit easier. Okay, and now we are ready to look. We want to look for a strain. So what I want to look to see what happened between pairs of points. So the change. Let's first look at the reference configuration. The side of the square in reference configuration, delta x1, that's the side which is along axis 1. It's parallel axis 1. It will be just simply xb minus xa. You agree with me, right? And the same way, if I look at the other dimension, I can write this. And I kind of assume that this is a square, so the lengths, these are vectors, and I took both to be L. Now what happens in what's going to happen to delta x1 in the deformed configuration? Well, this will become x prime 1, and x b goes to x prime b, so similar kind of formulation. Not to make any mistakes here. And it's useful to draw this to kind of show that. So this is kind of delta x1, it's a vector. Okay. And the same with delta x1 prime and delta. Okay. How about the length? Well, the distance between the points may have changed. This I call L prime 1. The other, like the distance between xa and xt may have also changed, but I cannot say that the changes will be equal. So although I assume that I started with a square element, I cannot say that it will turn out to be the length would be the same for both. So I consider the other one, maybe I write it next to it, would look nicer. And so this length is basically L1 prime, and this is L2 prime. Okay. So now, remember in the previous slide I talked about displacement. So now each one of these points has a displacement vector associated with it. So now let's use that relationship that I showed you before. Maybe I have to write it with orange here. So I showed you that x prime is x plus u. So I use that to relate the two. So I can say that for each point that I have, this holds. Okay. And now, we need to combine all of these relationships to relate the delta x1 prime and delta x1, but use displacement vector. So if I combine all of this together, all I'm doing is using the relationships that I have here in what I had before. Let me write it down, then you see. Delta x1 prime then would be, if I substitute for x prime b and x prime a, would be then delta x1 plus right. Bravo. Agree with me. You can all see it, right? I don't have to explain this. Yeah, great. The same thing. Well, you will see that these equations are pretty important. So here we have what is basically saying is that the change between the two vectors, delta x1 prime and delta x, if you look at the reference and deformed configuration, you can, that difference is equal to the difference between the displacement vectors, which goes to xb and xb and xa. So that's what it is saying. Now, I need to do one more thing. Since A and B, since we said that this element is very, very small, we can write the displacement at B using the Taylor series around A, because it's very, very small, the element, right? So we use that to write the displacement at B. We can write it as the displacement at A plus, and this you already know, the gradient of displacement evaluated at xa times delta x1, which is the difference between xb and xa, plus some higher order terms. This is just Taylor series expansion. You have seen the definition of gradient before. And if L is very small, and we assume that it's very small, if L is small enough, then the higher order terms are 0. So this gives us uxb minus uxa. So remember this, now we are just replacing uxb minus uxa with the gradient of displacement. So we are getting there. I need to change page, that's why I wanted you to remember what we had before. So, well, yeah, I did write this before, right? I don't need to write it again. So if you, let me go back, be more organized here. If we consider this as one equation and this as a second equation, so let's look at them a little bit more. So we have the relationship between delta x1 and delta x2 prime, delta x1 and delta x2, and uxb minus uxa, uxd minus uxa. Now, I just want to replace this uxb minus uxa.
Does it matter if your L primes are not small?
It cannot be. I mean, if you have a very small element, you are saying that it will become very large, then you go out of realm of elasticity of this class. You cannot use any of these theories.
So it doesn't work for like a rubber with a high...
No. So large deformation is completely a different story. So you cannot use that. That's a good question. But that's why I emphasize everywhere that the element is a small, L is a small, and everything is a small deformation. So everything is in the realm of a small deformation. We'll get there to formalize this a little bit more. So I didn't say that L prime is a small, but maybe I should have, because it should be a small. But later I will tell you that everything which is valid here is only valid if the gradient of displacement is a small, which implies that L prime will be a small. So yeah, so L and L prime are both very small, but we'll get there a little bit later. That's a good question. So everything we are talking about is a small deformations in this class. Now, look at this. So if I combine the 1 asterisk and the 2 asterisks, I get to this equation. So basically, instead of writing the two displacement differences, I just write the gradient evaluated at xa delta x1, and the same thing for the other direction. It's still evaluated at xa. Remember the definition of gradient from last week's, I don't know anymore when was the last time I saw you. But yeah, so this comes from this is clear to everyone. That's pretty important equation. Now, what do we see here? What did I start with? What did I start with? I said I want to get a strain, and a strain is related to the change of length and angle. And what we have here, this is a vector equation. So you have vectors. So I have the length. Look at the equation. I have the length in the deformed configuration is equal to length in reference configuration, right? Plus something times the length in reference configuration. So do you agree that whatever is this something, which is the gradient of displacement, it has something to do with the strain? That's because it's relating the change in the vector in the reference configuration to the deformed configuration. And the vector has both magnitude and direction. So it has information about both change of length and change of angle. It has a lot of information in it. So it's super important that you remember that the gradient of displacement contains information on a strain. Okay, so we are getting one step closer. Our goal is to relate displacement and a strain. And now we kind of know that, okay, the gradient of displacement seems to be playing a big role here. And this is what Kinsley was telling me like 10 minutes ago. And I said, you are jumping, really jumping the gun. You are going far ahead of what I want to tell you. Now, I am very careful here. I say this contains information about a strain, but I'm not telling you that gradient is equal to a strain. Do you know why? Why I'm not just saying gradient of displacement, perfect, we are done, this is a strain.
There's also rotation and translation.
Exactly. So this goes back to what Tom was saying, and just like Alex explained, I cannot say that this is equal to a strain because it turns out, as you will see in a moment, that it has both rigid body motion and a strain. So now, next, I want to find a way to filter out the rigid body displacement from deformation because I'm not very interested in that. If the body is just moving somewhere or rotating without changing shape, that's not a strain. I don't care about that. And we want to see how to do it. So for that, I need to rely on your information from before. The gradient of displacement vector. What kind of object is this? It's a tensor. So great. With all the closures, you still remember. This is a tensor. And now I have to remind you about your homework. What did we say we can do with any given tensor? We said we can write it as a summation of a symmetric and a skew or antisymmetric tensor. Remember? So since this is a tensor, I can do that. I say, okay, because this is a tensor, I can write it as a summation of a symmetric and skew symmetric or antisymmetric tensor. So this one is symmetric. This one, I think in the book it says antisymmetric. You sometimes see a skew symmetric. This is the same thing. And now, do you remember how these symmetric and skew symmetric components relate to the tensor? I give you 2 minutes to make sure everyone is awake to just try to download the information from your whatever knowledge, whatever you remember. Please remember. It was in the homework. And talk to each other. And this helps you not to speak. If you don't remember, just look back at your homework. I guess everyone, I think you all did it correctly. So you all know what this is. And write it down if you looked. So I write it quietly, and then you just turn your head and see if you wrote it correctly. Something like that. Oh, sorry. It's just to check that. In this case, John is awake and following everything. Yeah. Okay. So now, another check is try to write these two. Now I have a symmetric and a skew symmetric, right? Try to write these two equations using the comma notation. Don't tell me you haven't seen it. That's bad. And in using the comma notation, no, that's it. Index notation. Write it in terms of components. For this, you can't look back at your homework. What I'm looking for, let me be very clear. I want you to, in Cartesian coordinates, so let me ask my question correctly. So I want you to write using index notation. We write the components, right? These are both tensors. Right. Cartesian.
Yeah, I'll try to write it.
I've seen two independently one more in a different geographical coordinate. I just want to read So I've seen enough correct answers. I'm sure you guys are fine. So I hope that you have something like this. So remember, and if you haven't looked at the lecture, please do. Right? So, it turns out that this decomposition, if you are working with infinitesimal, very small deformations, is going to have very important implications. So just by doing that, you are pretty much doing what we set out to do, to filter the rigid body displacements from the deformations. But this is only true for small deformations. Going back to what Tom was talking about, if you have large deformations, if your research project involves looking at the missile hitting, going to the Mars, or how the deformation would look like, this theory falls apart. This decomposition is not doing what I just said it does. So it is only good for very small deformation, but it's very useful. So let's, now that we have found about this, let's go back at this equation. I'm not done with you. If you go back to this equation and try to write this, let's all of us try to write this in index notation, using now, basically substituting for gradient of displacement E plus omega. Right? So, and I'm not giving anything any names yet. This is just E, and that's omega. Yes, please.
So is that decomposed into like actual relative motion versus the rigid body motion?
We'll prove that. So we will show that this is the case. And it's only the case when the displacements are very small. So, how do we write the above equation? So if I replace, so substitute I have to, so this one has 3 sterics. Substitute we can see something like that. All I'm doing is just writing the vector equation in terms of component and substituting the gradient of displacement by E plus omega. So those are then tensors. Yes. So the I is the I component of the vector, and delta x1 and delta x2 are the vectors, remember, along direction 1 and 2. I'll go back and show you the figure. It is helpful to look at the figure from time to time. Did someone have a question? Yes, Jerry. So that's a good question. So E and omega, they are evaluated at XA still, right? Actually, I hadn't written it down, so I was just about to write. Where that was a good point. Everything is local because all the deformations are small. We use this locality to write the Taylor series expansion, so I cannot get away from it. If I do that, and that's why this is not valid for large deformation. Everything falls apart. I can write this in a little bit more compact. So let's look at the figure once, and then I write it in a little bit. So let's look at what everything is. So delta x1 and delta x2 are the two vectors along x1 and x2, and delta x1 prime and delta x2 prime are basically in the deformed configuration. And what I just wrote for you were the ith component of each. So I decided first to write that before writing a more compact way. So I write it here because I think it's useful. So I could just write both of them this way. Instead of writing 1 and 2, say, okay, the ith component of the kth side, basically of the small element that we had, would be equal to the same side but in the undeformed reference configuration, and then basically I'm not dividing it to E and omega, just the gradient of displacement evaluated at the point X times delta x k j. And I could have replaced u ij by e ij plus omega ij. So you can see how it works. And remember that this is valid locally, basically in the neighborhood of Now this becomes interesting when we look at a few special cases, because we want to now find out what are these E and omega tensors, and we do that by kind of experimentation. Yes?
There are rules on how far away from X
That's called engineering, right? So how small things are, what is infinitesimal, it really depends on the particular application and what is considered small for you. If you talk to geologists, I forgot about them. There are two people from geosciences here, so you know that in terms of allowing for errors, it's very different in engineering than, for example, in geoscience. What is considered for us a small error is very, very small. What is for you is considered a small error, for us is unacceptable, right? So it really depends on the application, the level of noise you have, and what you exactly want to achieve. Sorry about that. I forgot. I thought this is ESM. Everyone is engineer. Forgot about scientists.
So if you go back to the equation you just put in box.
Yeah.
So it looks like you could factor out the delta x1, and you have a 1 plus the gradient of displacement.
This is a vector equation.
Okay, so that was okay.
It will get a more and more familiar looks when you look at it. Let's look at now the special cases. Then you will see why this formulation it's very beautiful, because it really gives you insight to what is what. And I think it's much better than the way the book, if you look at chapter 2, the way they describe the strain, it's very strange, I think. It starts with giving you all the formulas and then goes back to the geometry, and I think you will like this better. You will tell me afterwards. Okay. Now, let's consider a few special cases. Suppose the case, so let's consider this case where E is 0, it's a tensor, and omega is also 0. Now if you look at the formulation, I think this is easy to see that in this case and these are vectors. So tell me physically, what does that mean? If E and omega are 0, it means that the gradient of U is 0. So you can see that delta x prime is equal to delta x. Physically, what does this mean? No deformation, but something else may have happened. I didn't hear it there. Translation. This is a simple translation. It can be no translation, but in the more general case, because remember we said vectors, they can go anywhere, right? If two vectors are equal, doesn't mean that they are the same place. They can be somewhere else. So this is simple translation. Not very interesting. Now you probably can see where I'm going. The next is consider another case. And I think I changed to a new page. So now consider, no, let's not call it that. Another case is consider the case where, now consider E is 0, but omega is not. So what do we conclude from this? We conclude that the gradient of displacement is just omega. In other words, the gradient of displacement is skew-symmetric or anti-symmetric. Now, this is important because we want to decouple these two tensors. So in 2D, if I want to write the matrix form of this tensor, how does it look like, an skew-symmetric tensor? Write it for yourself. I give you 1 minute. How does it look like? Exactly. And here, if I call this one 2, this is negative of that, right? So now, therefore, now I want to see what happens to delta x 1 prime. We are in 2D, so I have two components. Let's just look at delta x1 prime. Try to write it. We have the equation. So how does it look like? It will be, I write it without talking, so you have a chance if you want to write it for yourself. Let me write it from here. Make sure I haven't made any mistakes. No. So this is 0. This is 0. How much is delta x1, 1? Think about that little square, or look at it if you have it in your notes. L, right? That's, how much is delta x1, 2? In reference to the square that I drew a few slides ago. 0, right? And the same here. And this is also L. So, just L, right? So I don't write it down, but for delta x2, you can show that yes, Gerald. Let's go back to this figure. When I show you, then it becomes obvious. I wish I could have this figure somewhere and then do everything else. So delta x1, 2. Do you see why it is 0? It's a vector, like delta x1, and it's parallel to x1. So the first component is L, the second component is 0. So the vector delta x1 is parallel to x1. So it doesn't have any component in the second. It's kind of confusing, and that's why I drew a nice figure here and I put all of these because I expected that. It's because then you think, oh, 1 and 2, because we are using delta x2, and that's the other side of the triangle, so that's the perpendicular dimension. Any other questions? Great. So now that we have this, we go back and try to see what this means. I guess you have the intuition, you kind of can see, but we need to formalize it, especially regarding what Tom was saying. When we can say that we can separate the two, like rigid body displacement from deformation. And for that, it's very useful to draw, to see what that means. I mean, we have these formulas, what does it mean? And to draw this, it's not very hard. This one is not very hard. So let's draw our square again. And for the drawing purposes, let's take XA prime to coincide with XA. I don't want to draw another one, I just want to draw it right here. And let's assume that omega 1, 2 is negative. So what happens? So x prime A comes right here, and then what happens to xb? Where does it go? It goes up. Look back at the formulation. It goes up. How much? Right? Because it's negative L omega 1, 2. I assumed omega 1, 2 be negative, so it goes up. So this is delta x1 prime. Draw the delta x2 prime. Look back at the components. Make sure you know what everything is. I should have, I can kind of put a vector here. This is delta x1.
How does it look like? Well, because I just assumed that omega 1 you could have actually just put wrong. I assume that omega 1 is negative, that's all I'm saying. There are some something try not to use your knowledge from before really draw it, and because it's important to kind of understand what the components
This is what I change
Okay, I just draw it. And that's where we stop. So you saw, for the other one, if you look at the formulations after I said similarly, then you see that if we assume omega 1, 2 negative, xt has to go to the left. And how much is also L omega 1, 2 in terms of the size basically. And okay, I guess we need to stop here, unfortunately. We're almost done, but you kind of see where it is going. When E is 0, what do you see? Rotation. But it's not any rotation, and that's why I cannot just say we are done. It's infinitesimal rotation. We need to maintain that everything is small, otherwise everything falls apart. And that's where we start.